Hi, and welcome to the February edition of According to Pete. Last time, we talked about buck regulators. Today, we're going to talk about boost regulators. Everybody seemed to dig the last one, so we're going to do this one. Inductors. We should review inductors really quick. Here is a coil of wire. When you pass a current through a wire, a conductor, what'll happen is, as that current is ramping up from zero or changing at all, a magnetic field will create itself around the conductor. And so what happens when you first apply a voltage to this thing is that the current will ramp up slowly. And the reason why it does this is because as the magnetic field is expanding around each one of these loops, it cuts across its neighboring loops, and what happens is it creates an opposing EMF that suppresses the rise in current. And so it'll gradually rise up to here until you get to an equilibrium state. Now once you have that equilibrium state, what you have is a static magnetic field that runs outside of the inductor, okay? Now when you shut this current off, it'll do the same thing. It'll slowly kind of wind itself down. Same thing is going on. As you take the current away, this field will crunch back down into its original place, and so what you have is this thing will try to squirt that energy back out in the same way that it came, well, not back out that way, but back out that way. You'll end up with a plus here and a minus here instead of when you started. But it's that storage of energy that buck regulators and boost regulators, we're talking about boost regulators today, they depend on that sort of action. This is not a boost regulator, this is a buck. But Pete, we did that before. I know we did it before. This is just for reference, okay? And the last time we did this, we have our switch here, our inductor here, and our diode here. Now to review this, what happens is that you initially turn this switch on, ramps up some current here, goes through the load, this guy is reverse biased, and you've got current running around that way, and you've got a sense network here and a cap there. Now when you shut that off, when you shut off the switch, what'll happen is the magnetic field that is around this guy will start to collapse, and it will continue to push current through the load, okay, by means of this diode. And with the sense network going to your logic, you can tell roughly where your average voltage is, and you switch this thing at a high rate, and you PWM it, pulse width modulate it, and you end up with an average voltage, VF, which is less than your source, okay? That's a buck regulator. It's a very efficient thing. This is a boost regulator. Still the same. I got my load out here, I got my cap here, and I got my sense network here that tells me what the average voltage is at the output. These three components have changed position. Now I've got my inductor here next to the supply voltage. I got my switch from here to ground. Oh, that's scary. It's not that bad. And I have my diode here. Let's say I've got this switch closed. T equals 0. I'm just turning this thing on. When I've got this thing closed, what's happening is that the magnetic field is expanding from the inductor, right? This isn't doing anything, right? This is a switch to ground, so this thing is just ramping up voltage. And it's really operating in the linear region, like one small part of the linear region of the charge curve of the inductor, right? As soon as I open that switch, what's going to happen is that field is going to start to collapse, and it's going to start shooting current through the diode, through the load, charge up the cap, and back to the battery. In fact, how much voltage are you going to see out here? Well, you're going to have a voltage across this guy as the field tries to collapse, and it's going to be like that. And you've also got this voltage here. So you're going to have the additive effect of this guy and the field that's collapsing, shoving out through RL. The amount of voltage that develops by means of the inductor is directly related to how many turns the inductor is and how much the current changes given time. If I've got this switch turned on and I've got like a whole bunch of current running out here, when I turn this off, and this is only a little current, what's going to happen is the field will start to collapse, and if it collapses on a lot of little loops, it's going to make a bigger and bigger voltage. And if the current goes from a really big current through here to a really small current, that's a really quick transition. And it's the transition of the current that causes the voltage, the instantaneous change, okay? All of that to say, this is how a boost circuit works, okay? The same ideas about PWM apply here, all right? So you're gonna have a charge time and a discharge time, and it's usually going to be in the neighborhood. It depends on the logic that is driving this. In the case of my example, which is the MC34063, which is the part that we've carried forever on our storefront, it usually runs up to 100 kilohertz, and I've got an example around that guy I'll show you. This is one of the example circuits out of the MC34063 datasheet. This is the part that we carry on the storefront. This is a boost configuration as they have it set up, 12 volts in, 28 volts out, and they say it's going to have 87% efficiency. To compare this topology to the last picture I showed you, so here's your input. This thing comes with, you can sense the current, so it can shut down. So there's my sense resistor, and this is different. It'll come out in the efficiency calculations. They recommend a 170 microhenry inductor. I've got a 180. That's one we carry on the storefront. This guy feeds a Darlington pair, which is the actual switch. But what you have is the voltage in, goes to the inductor, hits the switch to ground first. Pin 2 is the ground for the switch. And then there's the diode, there's the load, there's the sense network back to vSense, which I didn't mark. That's pin 5 on their device. And a 330 ohm, a 330 microfarad cap on the output to minimize the noise. So just to plug this in and blind me and God, jeez, man. Now, as you can see, I've got 9 high power LEDs in series. Now, the point isn't to show that this thing is supplying a ton of wattage. It isn't. These things are rated for 700 milliamps apiece. I am running them in series. They're actually running at about 157 milliamps. But this is just to prove that you can run this thing up. Works just like the datasheet says, more or less. But these add up to about 27 volts in series, and then I've got a little current limiting resistor, about 10 ohms there, that doesn't get too very warm, that limits it down to about 157 milliamps. Let's talk about the efficiency of my circuit. Now, what you see here is a freaking mess, right? As I said a little while ago, the datasheet says you're going to get 87% efficiency out of this. I'm not getting 87% efficiency. To put it in equation terms, P out equals P, that's a P in, times efficiency, and that's going to be a number less than 1. If it's greater than 1, you're the greatest human in the world, because that is greater than unity. That doesn't happen. So my P out is 4.29 watts. And that is voltage times current, nothing special. I should also mention this 28 volts does vary according to what sort of load you put on it a little bit, so the numbers might not quite add up, but at the time, I swear to God, they all added up. My P in was 5.6 watts. So what you end up with is an efficiency of about 0.77 or 77%. So I'm 10% short of what the datasheet says. That's still really good. That's better than a linear regulator under most cases, all right? But why is it different? Well, as you can see from my circuit, this is not optimized. When you do this, when you lay out a buck or a boost regulator, switching noise is a thing. Relative positions of the components become a thing. RF becomes a huge thing. Check out my handy dandy poor man's RF loop just to see. You put this thing around my kludge of a circuit, and if you can see the scope over there, this is really noisy, okay? This is not an RF loop, but you can bet I'm picking up a lot of noise, a lot of high frequency spikes. This thing would wreak havoc under certain circumstances, okay? So you want to be more careful than putting it on a breadboard, but hey, I'm breadboarding it, so there you are. Other reasons, like I say, my component values are not optimized. I'm running a different inductor. My diode is not their Schottky, right? They want a Schottky in this place. I've got like a 1N4000 and something series, so it's a rectifier diode, not a Schottky diode. Totally not optimized for this. So I'm running less than 87%. Not a huge surprise. That is boost regulators, quick and dirty. You may have noticed that the last few that I've done all kind of revolve around inductors and how cool those are. And that is true. I think inductors are pretty cool. We sell all of one. And I can tell you, I think that's going away from our catalog because not a lot of people use it. The reason I dig inductors is because they have magnetic fields. And magnetic fields are cool, man! The next time I want to talk about a tune circuit and an oscillator, and I kind of want to maybe do something FCC not happy like about it. We'll see how this all pans out, but I got one more to do that's going to feature an inductor, and then I'm probably going to give it a rest and let everybody go back to their code and stuff and do their computers, blah, blah, blah. Thanks for tuning in. Put your comments and suggestions in the comment section, which is down now, or you can also email them to feedback@sparkfun.com with According to Pete in the subject line, and we'll look at it and go, that's a good idea, or that's a bad idea, and then we'll make a video, perhaps. There you go. Talk to you next time. Bye.